We could also represent infinite sets by their circle representations, just as we used the circle representations for small sets. For example, we could denote the set of real numbers, which is R, by this kind of a circle. Now obviously, because the set has an infinite number of elements, it won't be possible for us to enumerate the individual members of the set and represent them by dots, because there would be an infinite number of such elements. But we can still denote subset relationships using these representations. For example, we know that the set of rational numbers Q is a subset of the set of real numbers, because every rational number is a real number. So we can denote or represent the set Q by a smaller circle within the largest circle that is representing the set R. So all numbers that are within this inner circle are rational numbers. All numbers that are outside of the circle Q but within the set R are irrational numbers. So this region, this whole region, is inhabited by irrational numbers. They are not rational numbers, which means they cannot be represented as a ratio of two integers, where the denominator is of course non-zero. I had given you an example of that, square root of 2. Square root of 3 is also an irrational number, so is square root of 5. And even numbers like pi are examples of irrational numbers. Now within the set of rational numbers, we have a smaller subset, which is the set of integers. So I could draw another inner circle within Q, and this would be the set of integers z, because we know that z is a subset of Q. And we also know that the set of natural numbers n is a subset of the set of integers z. So we have another smaller circle here representing the set of natural numbers. So even the smallest of these sets, which is n here, is infinite. So the size here should not be interpreted as implying that this set is small. Each of these sets is an infinite set.